when we've been solving trig equations, normally we've been saying, oh, I just want solutions between 0 and 360 and so on. But if I didn't say that, there would be an infinite number of answers, because every 360 degrees there'd be another solution, or for the tan it would be every 180 degrees there'd be another solution, and so on. So we need a way of just generalising it, so we could generate, hence the name generalise, generate every possible solution, a bit like we do when we write down the domain for the tan curve. You know, we say, oh, well, x can't equal 90 plus 180k, where k is an integer, and then we can generate every one of those asymptotes. Same sort of idea. So let's have a look at, first of all, a sine equation. So sine theta equals some number. What does theta equal? Well, if x is greater than 0, then I know I'd be in either the first quadrant or the second quadrant. And the acute angle would be the inverse sine of x. Because if x is greater than 0, then the inverse sine of x would give me an acute angle. If I was doing that sort of equation, I'd say, well, therefore, theta is equal to inverse sine of x, or pi minus the inverse sine of x. Okay? So that's if x is greater than 0. But if x was less than 0, we now know that we're in the third quadrant, but the acute angle would not be the inverse sine of x, because we're now saying x is a negative number. To get the acute angle, we need a positive number. So it would be the inverse sine of negative x would be the acute angle. And the other possibility, of course, is over in the fourth quadrant. So my two answers then are pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. All right, well, inverse sine was an odd function, wasn't it? So inverse sine of negative x is the same as minus the inverse sine of x. So I get pi minus inverse sine of x, same as I got over here, or 2 pi plus the inverse sine of x. And then, of course, I could add 2 pi to each of those solutions. So the generalisation of that would then be, okay, if I've got sine theta equals some value, it doesn't matter whether it's positive or negative, because I end up coming with the same solutions, then it's going to be simply pi k plus minus 1 to the power of k inverse sine x. Because you'll notice here it starts off inverse sine x, but then it's pi minus inverse sine x, but then it's 2 pi plus inverse sine x. The next one then would be 3 pi minus inverse sine x, because we would add 2 pi to that solution. So the signs alternate. And that's why we need that minus 1 to the power of k in there, so we know whether we're adding or subtracting the inverse sine of x. So that's a way of generalising a sine equation. Let's see what happens with cosine. So we'll do it the same way. If x is greater than 0, in this case would be in the first quadrant, the acute angle would be the inverse cos of x, or the fourth quadrant. So I get inverse cos of x, or 2 pi minus the inverse cos of x. If x is negative, I'll be in the second quadrant, but again, now that x is less than 0, then I want inverse cos of negative x, because I want to create an acute angle. And the other possibility is the third quadrant. And so I'd have pi minus the inverse cos of negative x, or pi plus the inverse cos of negative x. Now, our rule for inverse cos of negative x, because we had the odd function shifted up. So inverse cos of negative x is pi minus the inverse cos of x. So this one becomes inverse cos of x. Oh, same as that answer. And the other one becomes 2 pi minus the inverse cos of x. Oh, same as that answer. So once again, it doesn't actually matter whether x is positive or negative. We come up with the same solutions. So to generalise this one, if cos theta is equal to some value, then it's simply 2 pi k plus or minus the inverse cos of x. Because we start off with naught plus inverse cos of x, but then we've got 2 pi minus. But the next one would be, I'd add 2 pi to this one, so I'd get 2 pi plus. So I get both plus or minus in those. All right, let's complete the set with tan. If it's positive, we know we're in the first quadrant or the third quadrant. And so I get inverse tan x or pi plus inverse tan x. If it's negative, I'm in the second quadrant, but again, the acute angle now would be the inverse tan of negative x. The fourth quadrant, so I have pi minus inverse tan negative x, or 2 pi minus inverse tan. Inverse tan, that was an odd function. So inverse tan of negative x, same as the negative inverse tan of x. So it becomes pi plus inverse tan of x, oh, same as that one. 2 pi plus inverse tan of x, which is the same as the first one because we can just add 2 pi to it. So once again, it does not matter whether x is positive or negative. I can generalize it. And we simply get pi k plus the inverse tan of x, where k is an integer. So they are what we call the general solutions of our three different trig ones. With the inverse sine one, some people split it up into 2 bits and have like this or this. I think the textbook might even have that somewhere, if you might see it in there. But I just think it's neater to write it as one solution and use the minus 1 to the power of k. All right, let's do them. Sine theta equals root 3 on 2. Notice it no longer is saying in between 0 and 360. It just wants all the possible answers. So theta will be pi k plus minus 1 to the power of k inverse sine of 3 on 2, where k is an integer. I know what the inverse sine of 3 on 2 is. So I can write that as pi k plus negative 1 to the power of k pi on 3. If I then said, oh, but what about if theta was in between 0 and 2 pi? I could now use this formula to generate solutions. So if I substitute in k equals 0, I would get pi on 3. If I was to substitute in k equals 1, I'll get pi minus pi on 3. Okay? If I was substituting k equals 2, I'm going to get 2 pi plus pi on 3. Oh, well, that's outside of the range that I'm looking for. So I know these are my two answers, pi on 3, 2 pi on 3. I'm not suggesting for a second that's how you would solve that equation if you were given sine theta equals root 3 on 2 in between that. But this is just demonstrating, oh yes, our formula can generate solutions. Let's try a cos one. So it'll be 2 pi k plus or minus the inverse cos of minus 1 on root 2, where k is an integer. Well, inverse cos of minus 1 on root 2 is 3 pi on 4. So there's my formula. So let's generate our solutions for between 0 and 2 pi. If I substitute in 0, I'll get plus or minus 3 pi and 4. Well, I don't want the minus one because we're just going between 0 and 2 pi. So I'll just have the plus 3 pi and 4. If I substitute in 1, I'll get 2 pi plus or minus. Well, in this case, I don't want the plus because that'll give me too many. So 2 pi minus 3 pi and 4. And there's our answers. So 3 pi and 4. 5 pi and 4. All right. Couldn't complete the examples without a tan one. So let's do tan. So that'll be pi k plus the inverse tan of 1 on root 3. And that is pi on 6. Generate those solutions. K equals 0, I'll get pi on 6. K equals 1, I'll get pi plus pi on 6. K equals 2, I'll get 2 pi plus, oh, well, that's too big. So I'll stop at the pi plus the pi on 6. So we get pi on 6, 7 pi on 6. Sine theta is equal to the sine of 5 pi on 7. Every possible solution. Okay. Still do it exactly the same way. So theta will be pi k plus minus 1 to the power of k, the inverse sine of the sine of 5 pi on 7. All right, 5 pi on 7, which quadrant is that in? Second is correct. Now remember, inverse sine then will not give me the answer 5 pi on 7. But second quadrant sine's positive, so I'm looking for the equivalent acute angle, and the equivalent acute angle would be 2 pi on 7. Okay, so there's our formula, pi k plus minus 1 to the power of k, 2 pi on 7. Now that's quite important. If I'd left it as 5 pi on 7, that formula is not going to work because of the minus 1 to the power of k. You get the negative on the wrong one, and so forth. Cos 2x is equal to the cos pi on 9. So we'll do the same sort of idea. Well, That now means 2x is equal to 2 pi k plus or minus the inverse cos of the cos of pi on 9. In this case, we're okay because pi on 9 is acute. So inverse cos of cos, that will cancel. But that's what 2x is. So divide by 2 and we get pi k plus or minus pi on 18. Remember when you're doing your general solutions, somewhere in your solution you need to specify, k is an integer. If you don't say that, then you're implying you could substitute anything in for k. So I could substitute in 0.273192486. 3, 1, 4, 2, 8. Anything really. Okay. 1f. Oh, geez, that doesn't seem like a lot of questions, does it? 9 to 11. 12 AC. Methinks I'm being generous.